Hey, good morning.
Good morning.
If you guys would please put your numbers. That's fine. Okay, but you have to take the puppies with you. All right, hey. Trying to get these children act right. Okay. So questions, let's start there. Cricket. One, two, who's number two? Oh, you're here. Hold on 1 second. Two, hold on. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9's Ethan, right? And 10. All right. Whoa, look at that. It's like I said it and it happened.
Hello.
All right, Chu, go ahead.
Oh, so for the assignment, when you say that it should be done with Keras, does that mean the independent module, or is it okay to use the sub thing in TensorFlow?
Yeah, I'm looking for the first one.
Okay.
I mean, honestly, let me say this. Honestly, doesn't really matter. Okay. The only reason it would matter is because we're going to go through each one of your codes together. And if your code is totally different than everybody else's, then it doesn't offer an instructional opportunity for the others to see, oh, this person writes their code that way, because then they're trying to learn the TensorFlow submodule. Does that make sense? So at least if everybody uses the framework Keras, if everybody kind of does that, then at least the codes are kind of similar in a way, right? So that way we can start to focus on some of the more idiosyncratic methods of coding that you each choose, and it will help other people get a better idea. Especially for you, Chu, because somebody who's a little bit better at Python, I would hope that maybe your code can help illuminate some techniques that others may not have utilized. Okay. So, other questions?
So if we're using the Keras sequential model, that's acceptable. Is that what you're saying?
Yeah. Pretty much everybody else, I think, can ignore the question she just asked. So did anybody do anything exciting over the weekend?
I just kind of relaxed. I met up with a couple friends yesterday, but
So nothing exciting, okay?
I took a test, so.
You took a test? Well, that's not exciting.
I don't know. I did start working on the assignment 1 and like mess with different optimizers and like number of layers. So there's
Yeah.
Oh, I do have a question about that actually.
Yeah.
When Dr. Lobo was talking about the layers and stuff, I mentioned that I added a whole bunch of layers in one of my assignments when I was playing around with it last
Yeah.
semester. And when I added the more layers, it actually performed worse. And he asked me if I used a bias. And I told him I didn't, but that's because I don't know how to add a bias to the model. Are we going to go over anything like that?
Let me say this. So to ask a question like that to me is incomplete. Let me say that. If it were as simple as adding a bias, this game wouldn't pay so much money. You know what I mean? It's considerably more complex in my opinion. So for example, did you use batch normalization?
Yes. Well, yes. Yeah, I used, or maybe I didn't.
So those are the kind of questions we're going to take a look at. Let me say this.
Okay.
The model that like I would use right now, that would probably, it's not old. Just kind of, it's older, but it's a pretty standard, very standard model called the VGG 16. And that's the one we'll use in PyTorch. Okay, that has 16 layers in it, right? More layers does not always equal better performance though, as I'm sure some of you are starting to see. And that's kind of the point of the experiment. So, you know, if that were true, then we would have hundreds of layers in our models. And, you know, what would be the stopping point? There wouldn't be one, right? So it's all about, that's why it's kind of an art and a science at the same time, right? In the sense that it requires experience. And after a while, you start to get an idea of this could work, and you try something and maybe it does work. And then you get a paper out of it, right? So one thing I did want to say is today we'll be meeting with Dr. Shaw at 2 o'clock from 2 to 2:30. Today's not a presentation day. Today's just kind of a day where he wants to meet with you guys because he was out of town last week. And so basically he just wants to meet you guys, right? He's just going to come in and say, hi, how's everything going? But I did want to say this. So when it is time to present, let me just take you through a quick process of how I think this should go. Let me see here. So all right, so come to the CRCV website. You're going to go up here to NSF projects. You're going to go to REU. You're going to scroll down. You're going to go to REU 2020. Now, this is pretty critical, okay, because how you do these presentations will determine your amount of enjoyment and fulfillment probably for the rest of the summer, okay? So you're going to go to REU 2020. Did you see what I did here with the Zoom background and stuff? I was trying to because the year before, you know, we had actually in person. So I was trying to make it look like we were all a little unit. So what I want you to do is you're going to come over here and you're going to click on someone like here, Matthew. And then you're going to go to week 1. You're going to look at his presentation. Okay. And you're going to steal his presentation format. Or not, let's say, you can use Christians, you can use Arushis, you can use Tamiks, Pedros, Callies, or Matthews. Basically, I want you to just go in and I want you to hijack their presentation format, okay? Right, that's exactly what they did for the year before them. So, right, this is kind of a process, right? So basically you're going to go in there, and then in addition to actually the formatting, I want you to also take a look at how they've presented things. In your first presentation, which I'm assuming will probably be this Friday, Dr. Shaw is going to want to see these things. He's going to want to see your performance on assignment 0. Okay. So he's going to want to see your classification performance on assignment 0. He's going to want to see preferably graphs if possible, right? Pictures, we talked about that. So assignment 0 was the MNIST classification assignment. Okay, then he's going to want to see your performance on assignment 1 in Keras. Okay, that's the CFAR 10 classification assignment. Performance means he's going to want to see your accuracy and your loss scores, right? And I can talk more in detail about that today. And then that's going to be for several different layers, are the different neural networks that you're going to create, right? Now, what we're going to do today is hopefully get you something with a better performance on those neural networks, because even though the assignment says do, you know, 3 layers, 4 layers, 5 layers, etc., ultimately the goal is going to be to get a better performance, because it's going to make him happy to see those numbers. Okay. And then yeah.
A question about assignment 0. So
Yeah.
I copied the code down that was given in the Jupyter notebook.
Okay.
Or wait, no, whatever notebook it was, perfect, like exactly.
Yeah.
And it ran fine. It was just that it gave like a much lower accuracy for some reason.
Okay.
I mean, I know that there's some variation, but it always gave a much lower score, and I'm not sure why.
Yeah, we can take a look at it. Okay.
Okay.
Yeah. Like I said, we have the rest of the week. Okay. And then he's also going to want to see your performance for assignment 0, your performance for assignment 1 in Keras, and then we're going to do the same assignment in PyTorch. Okay. So he's going to want to see those sets of scores. And even though assignment 1, for example, is supposed to be an experiment for you guys to see how more layers can help and even hinder performance, and more data almost always helps, right? That's the way this assignment's designed. It's an experiment for you guys to see that. Even though that's true, he's still going to want to see good numbers. Okay. That's just the way it goes. All right. Does everybody understand what I'm saying? So we're going to work together to do that. And it's not critical, but, you know, in the past, I've seen him say, you know, Zane, why are your numbers better than Ethan's? You know, oh, what did you do differently than he did? And, you know, so that's what so even though it's supposed to be a learning experience in that regard, numbers still matter. Okay. Okay.
I guess that does bring up a question then. What defines a good score?
Well, I wouldn't say anything defines it. It's all relative, you know.
Oh, okay. So like if for some reason, like, I don't know, I get like a 60 and everyone else is doing like up in the 80s, then it's like, oh, what am I doing then?
State of the art on CFAR 10. Right now, people are currently achieving 99.7% accuracy on CFAR 10. Right. So let's take a look at this. Papers with Code. This is a good website here. All right. So.
Excuse me.
Yeah.
Are we using CFAR 10 or CFAR 100? Yeah, but for assignment 1, it's going to be 100, right?
Incorrect. It should be 10, right?
I think
we talked about that, where I basically said, hey, the first line of the assignment says 10, but after that it says 100, but use 10 instead. And then I said, oh, it doesn't really matter, but probably 10's better. Do you remember that?
Yeah. I use 10, then I also use 100. I tried with both.
That's fine. All right, so here you can see VGG 11B, right? we're using VG. So here's VGG 19 with grad int. I mean, we're going to use VGG because it's just a super straightforward model. But any of these models would work, right? So let's go up here and just take. Now the thing is the further you go along here, like for example, this model here, I mean, you're probably going to get more and more confusing. So let's take a look at the code real quick and see what it's written in. So it's from Google Research. That means it's probably in TensorFlow. Training from scratch or blah, 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 blah. Anyways, we can go into this. Let me just take a look here. Yeah, TensorFlow. Okay. So that's not the code I would use personally. But anyways, okay. So that's just the point of this whole little thing that I'm showing you right now. Is this is how you find out what the state of the art on a certain data set is. Okay. Okay.
Oh, so the part of the assignment that was talking about varying the layers and said that there should be at least 3. Does the layers include the convolution and pooling layers, or is it only the dense ones?
Usually it's okay, so I guess technically it's both. The pooling does not, usually we say pooling does not count. Okay. Usually we say it's convolution and fully connected layers that comprise the quote unquote layers of a model. Right. But I think for the most part, the assignment's talking about convolutional layers, even though it doesn't say that. That's probably what I would consider. What was I doing? Lecture files.
I guess, in which case, like I tried adding a 4th convolutional layer to my model and I ran into an issue where the images got so small that it wouldn't run.
Yeah, right. That's true.
So I guess like I couldn't add a 4th convolutional layer if I wanted to, although there's probably something I'm missing, but
You could, but you would have to change the preceding ones.
Oh, if you did the padding as same, I think,
Right.
instead of valid, then I think it would work.
But it can still happen. Maybe this is not the one I want. Let me see. This is not it.
I think at some point I saw you had a Keras tutorial. I think it was for lecture files.
What did you say, Zane? Where was it?
Before lecture files, I think. I remember seeing a Keras tutorial. Yeah. Keras tutorial.powerpoint.
Yeah, that's good. Thank you very much. Yeah. Yeah, but I don't know. Let me double check which one I used last year because that one may be. Yep, I guess that's the one. Okay, so we can jump in here. Does anybody have any questions before we start this? Okay. So basically, and I've kind of told you this already, there's basically two deep learning frameworks that we're going to use, TensorFlow and PyTorch. Now, those are kind of the main ones. There's a high-level API for TensorFlow. It's called Keras. That's what we're going to use here. And basically what it does is it, in a way you can think of it as like a wrapper for TensorFlow. Basically it takes what could have been a lot of lines of code and it just simplifies them down into single lines, right? Like, so for example, you know how you can add the model, or excuse me, add the layers to your model, right? And you can just do model.add or whatever it is. That's not that simple in TensorFlow. It's considerably more complicated. These are some of the other packages that people use. Chainer has kind of like a cult following of people. I've only met one person ever that used Chainer. However, that one person is now making $400,000 at Netflix, so couldn't be that bad, right? Cafe used to be popular. It's not so popular anymore. You may encounter at some point, for example, if you want to use pre-trained weights or whatever. CNTK, never heard of it outside of this slide. So pretty much before all these deep learning packages came along, people wrote everything in MATLAB, right? And then this stuff came. Anymore, you may start seeing like, for example, I don't even really know what they're called, but you'll start to see these things on, they basically simplify the deep learning process for maybe non-deep learning engineers or non-computer vision engineers. So for example, you'll find these websites where you can kind of drag and drop type stuff. Have you guys ever heard of that kind of, setup? Those are, for companies, for somebody who maybe is in computer science, but maybe they don't understand deep learning or whatever. They just want to drag and drop a model in or whatever. So anymore, I see a lot of that type of stuff. It wasn't super popular when this was made in 2018. So we talked about this a little bit last time. I think I showed you guys that JSON file on your computers. Now, here's the thing. So this Thursday, people are going to review your research projects, your possible research projects. And once they've done that, you'll get to choose which research project you want to work on. Now, some of the people that you'll go to work with will work, most of them will work on PyTorch. Some of them, on the other hand, will work in TensorFlow, okay? So that's kind of in my mind, the justification for keeping Keras in this whole tutorial is because it isn't just something to help you get introduced into the deep learning process. It is also good because you could probably take some of that learning with you to your research projects, especially if they're working on TensorFlow. TensorFlow is currently at something 2.x. I don't know what the version is right now, but to my understanding, version 2.0 is a lot more user-friendly than the 1 series. So, but anyways, all of that to be said, we talked about the back end of Keras. You guys remember that, where I showed you that little file and it said backend : whatever. We're going to use TensorFlow, but you can also use Theano. Theano is not used a whole lot anymore, to my knowledge. I don't see it all that often. But again, if somebody learned Theano years ago, when all these packages were coming out, they probably stuck with it, right? why use Keras? I think I've already talked about all this. Hmm. I'm not sure how this is relevant at all. Skip that. This is important. But I think there's a picture here. Here we go. Okay. So in general, I would say this is probably one of the more important things that we'll cover. Okay. So this is kind of, I would say today is kind of where the actual theoretical side starts to blend with the practical side. Okay. And I think some of you guys encountered that over the weekend where you started, you know, saying, hey, like, I'm writing some code, but I don't really know how to change that code because maybe I don't understand the theoretical side as much, right? That's why I wanted to just get some code, get it running, and then we'll go from there. Now, in general, the way this whole process will work is, now see with data sets like MNIST and CFAR10, right? Those are often called toy data sets. Toy data sets, first of all, because they're not all that big. And because they're really just manicured already for your use. So you're not going to have to actually go in and do any data processing for the most part, because it's going to come to you already cleaned up, already labeled, already, you know, put on a little platter for us to use. Like, for example, you can just import it in a single line. You don't have to do anything. That's not going to be true for your research projects, most likely. Most likely what's going to end up happening is you're going to have considerably more complex data sets, most likely comprised of videos. And you're going to actually have to do some data cleaning to get that all ready for use. So the first thing here you can see is that we're going to prepare the input. Whether it's images, videos, probably won't be a lot of text for you guys. Audio, whatever it may be. I think I'm actually the only person in the lab that's ever worked with audio. So anyways, whatever it may be in the end, you're going to have to prepare that input. Okay. That's usually going to be a single file in your project. What do I mean by that? Well, let's take a look at something real quick. So usually a deep learning maybe I can show you something that's a little bit better over here. Okay, so usually any deep learning code that you're going to write is going to have several files associated with it. Okay, so for example, here we have main, right? That's always going to be the main, you know, the main place your code is running. Okay, from there, usually you'll have a separate file for, it's called for data. Right? Inside of that data file, you're going to basically do all of the data preparation required for this step here. Okay. That single file is going to output just your data. So you know how, for example, in the Keras where you can slide, you can load those data sets just a single line at a time. Well, in this case, that's what your data file is going to do. It's going to prepare all the data and it's going to allow you to call in your data for that just kind of single line idea, right? So if you take a look here, so in my main file, from data, import everything, okay? And when we do this, it allows me to import all the variable names, etc., right? The namespace, whatever. So let me come down here now. So this little section here is going to take care of loading my data. right? Now this is in PyTorch, so we'll do more with the Keras stuff in a minute. But my point is that if you look at what actually is loading my data, what's actually loading my data is pretty much these lines right here, okay? And you can even ignore this line right here. So in other words, it's like a total of 6 lines in my main code. But if you look at the data file here, this is everything that's required to get that data ready to go. Okay, does that make sense to everybody? So this is just kind of the overall structure. So we're gonna question? No. All right, then define the ANN, CNN, whatever it may be. Okay, so then we're going to define the model that we're going to use. Okay, so then you're going to have a separate file for your model like this, model.py. Okay, now if you look at this file, right, model.file, you're going to see that in here, this is where I'm going to build my VGG model. Okay. Now, how I do it is kind of irrelevant, but you can see this code all here is what basically builds that model. And then in my main, again, you can see from model, import the VGG model here. And then I'll show you where. So here, model, right? So this is where I instantiate that class. Okay. What is the point of what I'm trying to tell you? So you're going to have separate files that are responsible for taking care of the data, one for taking care of the model. That's pretty standard. Now, if you're doing something a little bit more Wild West, you may have a loss file here. You can also have your own utilities file, right? And in this utilities file, you can just define some little functions that you use. That way you don't have to write them all in your main code, okay? The whole point of all of this is to keep your code clean for you and others to read in the future so that it doesn't get overwhelming, okay? So let's take a look at, so we've basically, this is responsible for an entire file, okay? Data, we'll call it data or dataset.py. Then we're gonna have another one over here. This is gonna be the model, where you're gonna build your model. You're going to choose your Optimus Optimizers, right? So in most cases for us, at least while you're with me, we're going to use stochastic gradient descent, okay? That's just because it's so standard, you know, and it usually performs good enough, right? Then we're going to choose something, then we're going to choose a loss function. These two things, the optimizer and the loss function, unless, like I said, you're doing something Wild West, then if you're just using a standard optimizer and a standard loss function, these are going to be defined in your main code. So let's take a look at that. Now I know I'm showing you this stuff in PyTorch, but it's very conceptual. We're not actually talking about code yet, okay? So look here, optimizer and loss, right? Now I'm going to make sure all of you have this code along with other codes. That way you can take it with you and have your code library, you know, good enough. Plus, I like to keep my code pretty organized, so it's pretty explanatory, right? But optimizer and loss, here we're going to do those things right here, okay? So it takes very little code to do that. So these two things are going to happen in your main code, okay? And then you're going to train and evaluate, which will, of course, happen in your main code as well. Any questions about this so far? So now, in general, this is the pipeline that you'll follow. But what I want to say is that this pipeline can also be represented by the structure of your files, which is the way that I keep track of it all in my mind, okay? So this little process, you don't need to memorize this little graphic. What you do need to know is that my code should be defined or designed in such a way that I have a main file, a data file, a model file. And then from that point, you can kind of keep track of how it all works. Is everybody clear? Sanjay, did you have a question?
Yeah, will we later on go over what exactly the loss function is?
Yeah.
Because I'm a little,
Yeah, that's okay. It's totally
yeah,
okay.
I'm a little lost on that one.
Yeah, and I also wanted to say this, and everybody in the world, most people don't agree with my opinion on this, okay? But I don't think for the most part, you guys have to understand at a deep theoretical level what's happening in order to do a lot of this stuff. Okay. Now, in order to make something new or something novel, or to get down into the nitty gritty and start, really changing stuff out. Let me maybe use a car analogy here. And Michael may tell me I'm completely wrong because he's the real mechanic here, but that maybe that's the point. Okay, Michael's the real mechanic here. He's got 10 whatever years of experience. I have zero mechanical experience, right? However, I've replaced the starter on my car. I've replaced the radiator on my car. I've replaced air filters and the battery and other things, right? Why was I able to do that? Because I went on YouTube, I watched a video, and I stayed at the Holiday Inn last night. But but that's because I understand. I watched the video. I saw how to do one little thing. Now, let's say I wanted to go in and I wanted to. This is probably making me sound stupid, but let's say I wanted to go in and change out the electrical system in my car, right? And not only change it out and replace it, but modify it, upgrade it, whatever, all that kind of stuff. Now we're starting to get a little bit more in depth, and that's where Mike would have to come in and say, hey, let me handle, does everybody see what I'm saying here? You find some code online, you just kind of can copy what other people do and start to get an idea of how they structure things and try it, trial and error, okay? So, you don't necessarily have to have a super deep understanding just yet about what the loss function is, but it'll come. We'll talk more about it later. Blah, 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 blah. Ignore all this. This is all unnecessary here. So let me actually pull up. Let me see what projects I have here. Hold on. Let my puppies in. I'll be right back. Okay, sorry about that. Yeah, switching computers. I had everything so nicely organized on my other computer. So sorry about a little bit of disorganization here. It's kind of frustrating. Assignment 0. That's not what we want. I guess I won't jump into it just yet. I was going to actually pull up some code, but we have the afternoon for that. So basically, there are two types of codes there are two types of models in Keras: sequential and functional. Okay. Sequential, and you can kind of take this thought process with you to all other frameworks. Okay. This is my point. You can either, for example, add things in a method like this. Do you see how I've model.add, model.add, model.add? And I think the syntax has changed just a little bit for Keras, and that's okay. But the point is the same. You can either build a model where you literally write hard code each single layer of your model, or you can do it in a functional way where you write a function and say, if I call this function, add 3 convolutional layers with, blah, 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 blah. Okay. Here, okay, this is going to actually, this is why this is kind of so nice, is because actually, let's pull up our assignment 0 code. How about that? Okay, let's come down here. Okay, so I think this is probably actually a little bit better than the slides here. So build a sequential convolutional model. Now, the functional method of defining your models is a little bit more advanced, okay, and is not always necessary. So I want to say this. You may find yourself at a point where you say, I want my code to look as clean as the functional code, right? That's not always going to be necessary. Your first goal should always be to get some code running, period. Okay. That way, when you have your meeting with Dr. Shaw, you can say, hey, I got this code running, because I can promise you now, Dr. Shaw is not going to say, hey, does your code look good? Nobody's going to care about that. Okay. So the first thing you should always do is get down and dirty with your code and just get something running. Okay. So here, what we're going to do is we're going to define this sequential model. You can see model.add, right? And the syntax is probably a little bit different now. That's okay. Here we can add these convolutional layers here. We're going to add the max pooling, and we're going to add these dense layers are fully connected layers. Okay. Again, at this point of the game, I don't expect you to completely understand what a fully connected layer is. You should start to get some idea of what's going on with those things, but I don't want you to get overwhelmed and let it put up a wall and stop you from moving forward and running code. Okay. Like I said, the most important thing in this game is to get good code running so that when you start to understand how everything's working, you're already on the ground running. Your wheels are already turning, your code's running, and you can start to say, I got a little bit of a deeper idea of how this works. Maybe I can make this other modification. Does that make sense to everyone? Don't let these mental blocks stop you from getting good code running, okay? There's too much on the web as far as the code is concerned for you to not do that. Now, enough of that. So now in Keras, here's what we're going to do. Model.compile, okay? Now you can notice here that in basically what's a single line of code, right? We're going to tell our model what loss function we want to use. We're going to tell our model what optimizer we want to use. Add delta is just another optimizer, could be SGD, right? And we're going to tell our model what metrics we want to use, and in this case, accuracy, right? So you can see that this is an incredibly simple and straightforward way of doing things, right? Now, even in the PyTorch code I showed you where we used 2 or 3 lines, that wasn't all that complicated, right? But Keras is much more simple than the TensorFlow version, okay? That's the point of what I'm trying to tell you here. Now, this is where things get really, really considerably different. So let me Okay, so now in general, right? And I can't compare TensorFlow code for you because I don't write in TensorFlow. I don't think I've ever written in TensorFlow other than Keras. I've used that. But what I can do is show you just in general in PyTorch, which in my opinion is always going to be better than TensorFlow. Okay, but here's the point, right? So notice here in Keras code, model.fit, right? This is where we're actually going to train our model. Okay, model.fit, we're going to put in our X data. We're going to put in the corresponding Y data. So X data means like all of the images. Can somebody tell me what the Y data means?
The labels of those images.
Exactly. So let's say I had 10 images here, 10 images, and then these are going to tell me what each one of those images are. Is it a cat? Is it a dog? Is it a bird?
Oh, so the classes?
Exactly, the classes. Yep. Okay. Batch size, boom. Batch size, we can talk more about that today. Epochs, verbose, ignore. Validation data, this is the test data, right? So this is train, and this is basically test, okay? All of that's happening in one line, right? Now, of course, you've returned here, so it doesn't happen in one line, but for all intents and purposes, it's one line, okay? So you're gonna train your model in one line of code. That's in Keras. Everybody with me? Okay, now jump over here. Here's what you're gonna do. Actually, you're kind of training and validating, training and testing. And let me make sure this isn't Dr. Lobo here. Request for presentation on. All right, I'll have to deal with that later. Okay, so to compare now over here, look, this, so in training, this is how many lines of code that it's going to take to train the model in PyTorch. Okay. Now, it's not that many lines of code, right? But you can start to get an idea of what's happening on the inside behind these single function calls, right? Model.fit. All of this is happening behind the scenes, right? So that's just for training. Then you're going to have the testing function, which is about the same thing, right? And then you actually have to run it, which happens down here. So basically all of this training all the way to the training function, right? All the way. All of this code here happens in a single line with Keras. Okay, so that's the benefit of Keras. Now, one of the takeaways with Keras is the ability to, the modifiability, okay? In PyTorch or TensorFlow, you can actually get into the guts of it and make some changes. Whereas with Keras, that's not always possible. But at this point, any of the models that you're going to want to run, you can simply do like this, model.fit, okay? So stacking layers. So in the sequential model, right? In the sequential model, all you're going to do is you're going to pretty much hard code each one of these into the model. Now, what's nice about this, let me see where I built my model. Here it is. Okay. What's nice about this, okay, this ability to build models sequentially like this in Keras, is that in PyTorch, you actually have to do some computation in order to determine the size of things from one step to the next. Okay. In Keras, you can see the numbers that it requires are considerably more straightforward. Okay. So it's a, it's a give and a take. So basically Keras is going to be more, it's going to be high level, it's going to be cleaner code, it's going to be less advanced, right? It's going to allow for less flexibility. So you can hard code these in here, model.compile, boom, we're going to set up the parameters for our model. And then you're going to train the model.fit. Linear stack of models. Okay, I guess I can say this. So now consider this neural network here. Okay. This neural network is good from the picture, I can tell that for the most part, it is a good candidate to be defined by, hold on one second. So this model here is a good candidate for using the sequential model or the sequential structure inside of Keras. Why is that true? Anybody want to take a stab?
Because you have like a simple input and a simple output, maybe
It's
like
exactly
a
right.
defined flow, I guess.
Yeah, yeah, nice linear sequential flow, right? If you look at it, you can see do this, then do this, then do this, then do this, right? So it's kind of this straightforward shot. Now, that's not true in all models. So the sequential style model won't be sufficient. So we, which is why they come up with the functional model, right? So like Ethan just said, multi-input or multi-output models, right? So let's see if we get a nice picture here. This is perfect. Here we go. So here we have a model, right? So we're going to input a 3-tuple here, right? So you're going to send in an image to this AlexNet here. You're going to send in the image to this AlexNet here, and you're going to send an image into this AlexNet here. However, they're going to be sharing weights as we go along. Now that's irrelevant for what you don't need to understand that process. What you do need to understand is we have multiple inputs. So there's not this nice straightforward linear structure. Okay, this idea of stacking things is not going to work for us here. Okay. Unnecessary for our purposes. So this is good. We can actually talk about this. Okay. So this picture here in my mind perfectly defines what it means to be a sequential model, right? Even though we saw this fancy little picture back wherever it was back here, right? This picture here, at the end of the day, that's not what it actually needs to look like in my mind. Okay. If I'm going to publish a paper, this is what my model should look like. However, this is what it should look like in my mind. Okay. And this is what it's going to look like if you build your model sequentially. You're going to have model.add, right? Okay. So a couple things we want to talk about here. Fully connected layers. In Keras, that's what they're going to call a dense layer, right? For those of you who have started writing code in Keras already, is that still the syntax?
It is still called dense, yeah.
Still called dense, okay? Now, the dimensions of what we're inputting into our models is where things can get a little bit more complicated. And we'll talk more about it as we go along, but the general idea is this, okay? The general idea is that the structure of how we're going to input this data into our model is going to be the number of samples here in train. I don't know why you would call this in train. This is the number of samples that we're going to have. This is the height of the image. Where's my laser pointer at? Okay. This is the number of samples that we're going to have. This is going to be the height of the image. This is going to be the width of the image. And this is going to be the number of channels in the image. Let me see here. That's what I just said. Okay, so can somebody tell me what it means, channels? Does anybody understand what that means when we say channels?
RGB.
Yeah.
Yeah. RGB or grayscale, for example, right? Let's try you, Chu. Chu, what does that mean exactly?
The color, the image is specified by 3 number of values, and each of them corresponds to one of the color channels, and you have to combine those together to get the color image?
That's exactly right. That's exactly right. So in the case of a grayscale image, right? In the case of a grayscale image, you're going to have a single channel, right? Now, here's how you can think of it. A single image, let's say I have an RGB image. Okay. Now I need a third hand, even though I don't have a third hand. Okay. So just bear with me, right? Let's just pretend my phone. This is my phone. Okay. This is the third image, right? An RGB image is going to look like this. This is going to be 1, this is going to be 2, and this is going to be 3. Okay. Now, if I was to decompose this image and I was to look at it in kind of an exploded view, and I have these 3 things, I'm going to have the red channel, I'm going to have the green channel, and I'm going to have the blue channel. Each one of those channels typically is going to have values from 0 to 255. Okay. 0 to 255. Now let's just Google a little picture here.
Is it with 0 being the brightest and 255 being the darkest?
RGB image.
So I guess we're using 8-bit color depth then.
RGB image decomposed. Here we go. Lena, I think this is the lady's name, Lena. Right. So let and maybe everybody's not clear about this yet so far, and because I don't know, if anybody else has talked about this with you so far. Basically, every single image that we're going to work with is just a matrix. That's how you can think of it. Okay. So to kind of take away some of the magic of computer vision, all we're doing is working with matrices, right? So here, at its simplest level, you're going to have a matrix that looks like this. Let's say it's square for our purposes. And it's going to have, let's say it's grayscale. So in other words, each one of those images is going to be 0 to, each one of those values is going to be 0 to 255. So let me look up a grayscale image values. If we get a nice little picky here. Here we go. This is nice. I like this image actually. Can everybody see this? This is brilliant. Okay. So here's the first, and isn't it funny that like our human brain can tell that this is Abe Lincoln? Don't be annoying. Brr. Okay. So here's the idea. So you're going to start with this image, but each one of the values in this image, 0 to 255, is just inside of a matrix. So at the end of the day, this matrix is actually what we're dealing with, right? There's actually no image. Our model never sees any image at all, right? So that's just kind of like this. It's really not as magical as one may think. All our model sees is a matrix. That's it. You're just putting in this matrix of values. And each one of these numbers has some equation that acts on that, okay? So as you can see here, these black values are 0, right? And then let's look for a white value. Let's see if we can see something. I don't see any 255s here. I see a 252, right? Basically, the point is black is 0, and then white is 255. So they go anywhere along that spectrum, okay? Now, compare that to the RGB image that we looked at over here. Each one of these values is going to go along a similar range, right? 0 being probably black, actually. And then, or close to, I guess it's a very deep shade, deep hue of red, deep shade of red. However, when we take these 3 matrices, we're going to put them together and they're going to look like the image. Now, it kind of blows my mind that that's possible. When we put those 3 things together, that it's going to happen. Now, why do I talk about all this? The reason is this, is that when you look at the input structure of how we're going to put our images in, you have to kind of throw away the idea that channels actually are a form of depth as well. Okay, does that make sense? When you look at an image, right, I guess my phone was actually here with us. When you look at an image, there's actually those 3 layers. There's 3 channels happening, right? Those 3 channels are a form of depth itself, but we don't treat it that way, okay? So when you put this into your model, you can, let's say we had 10 images here. So I have 10 images, 1, 2, 3. So it looks like this. Here's a stack of images. Is everybody cool with that? Right. Each one of those individual images has a shape like this. And each one of those individual images is itself has 3 channels. So it has its own depth, but we don't think of channels that way. Is everybody good with this? Okay. This will become more useful as time goes on. Okay. So here we're going to generate some So I guess we're going to build this model over here. Okay. Now, I know that a lot of you, I encouraged a lot of you to kind of get started on the assignment already. But for those of you who didn't, I'm sure there's someone here. This will kind of help out. Okay. So the first thing we're going to do is we want to build this model, right? So what we're going to do is we're going to input images, which are square, right? 100 by 100, each with 3 channels. So they're RGB images. And that's going to look like this: 100 by 100 by 3, right? This is just the size of each image individually, right? Everybody good so far? Okay. This applies 32 convolutional filters of size 3 by 3. Okay. So what we're going to do is we're going to do model.add. We're going to add a 2-dimensional convolution. Here, the filter size is going to be 3 by 3. Okay. Does everybody remember what that means? The filter is that little box that moves along your image and does the calculations. Right. There are going to be 32 filters. We're going to use the activation is the rectified linear unit. Did you guys talk about that with Dr. Lobo? Right. It just looks like this. Basically, rectified linear unit is a fancy way of saying throw away the negative values and keep the positive values. That's it. Okay. And you're going to say my input shape is 100 by 100 by 3. Okay. So everybody good with that? Okay. Then you're going to do another one of those. You're going to add another. So if you look over here, we're building this, right? Convolutional. I want 32 filters. I want a convolution with 32 filters. So we're going to add another convolutional layer with 32 filters, 3 by 3 by 3, right? We don't have to put the input shape anymore because in Keras, it's going to infer what the shape should be from the previous layer. Okay, that's one of the nice things here. That's not true in other frameworks. Here we're going to add max pooling. Leah, can you tell me what max pooling is? Do you remember?
Calling me or are you calling Leah?
Leah.
Yeah, I will talk.
Leah Howells, please.
Oh, sorry. I thought I just muted everything. It was like the. I can't remember. It was like the.
Okay, so everything pretty much, okay, convolutions and pooling all happens basically with filters. Okay, filters are just miniature matrices that slide along my larger matrix and do some calculations along the way. Okay, so to take away some of the magic here, there are no images inside of my model. It's just matrices. Okay. Sorry, it's very challenging because my dogs, they just, one of them's really good and doesn't whine. And then the other one, so the terrier, the little dog, the Yorkie, he'll just come in here and he'll just sit with me all day. He's just a good little boy. But my pit bull, if I let her in here, she just stands at me and looks at me like this and just cries the whole time, like she wants me to pet her. And so anyways, okay. Yes, so max pooling. Basically here's, okay, so you have this matrix. Let me see if I can draw on this thing. Pen, can I draw? Noise. Let's undo that. Okay, so let's say I have this image. Meow, meow. Okay, and let's do, now, this is going to be a really small image, okay? It's going to be 3 by 3. Is everybody cool with that? Okay, then what I'm going to do, what is this? Nope, don't want that. Pin color. Let's do blue now. Okay, so for this max pooling step, all right, then what I'm going to do is I'm going to take a, so it says pool size. That's not a pool size. That's a kernel size or a filter size, right? So what I'm going to do is I'm going to take a 2 by 2 filter starting right up here in the top left corner. And I'm going to put it over here. Now, whatever values are inside of this little region here, let's say they were, let's do 2. Let's do 5. Sorry, this looks really bad, but let's do 5 and let's do 7. Okay. So when I do this max pooling step right here, what I'm going to do is I'm going to take a 2 by 2 filter. That's the blue thing. And then when inside of that little matrix there, all I do is max pooling is just a fancy name for taking the maximum. So what is the maximum number in this little area? It's going to be 7, right? So this is the winner, winner, chicken dinner right here. Okay. So what this is going to do, it's going to output to, can somebody tell me after I do the pooling, what's the shape of this guy?
It'll be a 2 by 2.
That's right, 2 by 2.
Yeah.
Right. Okay.
I guess, are we storing in the top left or? Actually, wait, it doesn't matter because we're gonna be shrinking it anyway.
Okay. So this is going to put out a 2 by 2. I'm going to show you why he knows that. Okay. Okay. So now from this region here, Leah House, you with me? Okay. From this region, I looked at the maximum. It was 7. Okay. So that means I throw away all this other stuff. Throw it away, throw it away, throw it away. And I'm going to take the maximum number and I'm going to keep it. That's the number I want. Okay. Then let's say I move my filter over. I'll do it in a minute. So here I have 8 and 1. Okay. So then I'm going to move my filter over 1. I'm going to do it in green now so you can see. Okay. You guys think I should do it in green or should I keep it as blue? What do you think?
Maybe keep it as blue because then it's like we know that's the filter.
Okay. All right. So now I'm going to take it and I'm going to put it right here. I'm going to move that guy over 1. Right. So basically I just slid it. So it started here and then I slid it over. So it's like this. Start here, then I slide it over. Okay. Slid it over. And then what's the largest value inside of this area now, Leah House?
8.
Okay, good. So I'm going to keep that number, right? So then I'm going to keep that number. Okay. And then whatever, I would do the same process over here. And then I would do the same process in this little region here. Does everybody feel comfortable with what max pooling means now?
I have some comments.
Please.
Whenever you're- Okay. So I was doing a bunch of reading yesterday, and the max pooling on Keras with the model.add with the pool size, that first number 2 tells you the size of the kernel or whatever your box that you're going to be max pooling from, and that second number is the step size. So
oh, very good.
With
very
what
good.
Robert was doing, he moved it 1 step. That would actually be a 1, where that second number is a 2. In his example, that would have been a 1.
Very good. Very good.
Oh, so that might
and then
be my, I'm sorry, but that might be the solution to add more layers to my model because it shrunk it so much. Huh.
yeah, so also another thing about max pooling, in the paper that Zane, or not paper, but the post that Zane put a link to, it talks about what the purpose is of max pooling. And I was very confused about this before, but max pooling, the whole point is to avoid overfitting. So if you have like a really big picture, small differences can be overfitted to and make it hard to make the image able to get a good answer. But if you do a bunch of max pooling, you can shrink it down and make it so you're less likely to overfit on it, and that way you can do a better get a better accuracy on it. So with the little 32 by 32 images that we're looking at, doing a lot of max pooling is probably a bad idea, just because they're already fairly small. But that's just my idea on that. And then another comment, Dr. Lobo made a really big point to call the images tables rather than matrices. But I don't really understand why he was saying that, because I mean, in reality, they, in my opinion, are matrices. So, but he made a big deal on that.
I mean, probably because at some level, you know, that's a matter of personal preference. I've never heard anybody else say that. But you know, there's probably some intuition. He has some intuitive reason for what he's saying, probably. If I had to guess what that is, it's probably because at some level, especially once we start doing video, and you're going to have, actually, how funny Dr. Lobo is calling right now.
I think the reason he made that distinction is because he doesn't want anyone to consider any like linear algebra properties of these. Like it's just a table of numbers. There are no like, you know, determinants or whatever of the matrix. It's just an array.
Yeah, I think that's a good point. That makes a lot of sense. But personally, I feel like that kind of I don't think that, I mean, in my opinion, I don't think that's really useful, because a lot of the things that we do to the table are specifically, you know, linear algebra and matrix algebra. So in that sense, to me, it seems like, you know, I think he's, you know, maybe going a little overboard saying that, but maybe it's just to try and make it seem easier for the you know, people that are new to it.
Yeah, I could see that. Maybe it's so like, yeah, because it does get treated as a matrix down the line, I believe. But maybe it's to say that, hey, you can't use like straight up matrix properties on the image, like just by itself. Like maybe when you actually do calculations, sure, but for the image just by itself, it doesn't have any of these properties because it's just a table of values.
Yeah, I totally agree.
I'm gonna get some water. You know what they say, hydrate or dihydrate.
Okay, guys, sorry about that. Can you hear me?
Yep.
All right, good. Yes, Michael, thank you. Very good point about the syntax here, okay? Because I'm not, a Keras Pro, that's a little thing that I could have missed. So that's very good. Thank you. So basically, just to clarify what he's saying, does anybody not understand what he's saying? So basically, what he's saying is this first number here, assuming that's correct, and I'm not saying you're wrong, I just don't know for sure, but it's probably true. This first number here defines the square size of this blue thing, this blue filter, okay? So in other words, 2 means it's square, and it's 2 by 2. The second step, the second number says, when I'm here, remember how I moved my little blue square over 1 unit? Instead of moving over 1, I would move over 2. Well, in this case, it doesn't work very well because there's not a place to move over. I would be hanging off the edge, right? But let's go ahead and double check that while we're here. Keras, max pooling. Keras, max pooling. Pool size, strides. Down samples in blah. Yeah, that's right. We know that.
Well, it showed pool size being the tuple and then strides being something separate.
Mm-hmm. Arguments, pool size. Integer or tuple, window size over which to take the maximum. So I don't think that was actually true, Michael. 2 by 2 will take the max value over 2 by 2 polling window. Yeah.
Oh, so it is like you can specify a non-square shape, and strides is actually the step size.
That is the way that's what I'm reading here.
Yeah, that's what it looks like.
But then under strides, it also says that if you don't specify it, the default argument is pool size. So since you didn't specify it, it should shift over 2.
Yeah, I see what you're saying. So for example, I guess what you're saying is kind of true in the sense that if you don't specify strides, it defaults to that number, right?
Yeah, I'm trying to look to see where I was reading that because I must have misread it or something, but I thought it was pretty clear.
Well, and that's okay. I mean, it's totally okay either way. Here's the point. The point is that this is a good opportunity to see that, like, I mean, I've been doing this stuff for years. I mean, I have my own flow. I don't do Keras or whatever. So you can see, like, I'm not the world's greatest pro at Keras, and that's okay because it doesn't really matter. I know what I need. I know where I need to go to find the answers. That's the point, right? And that's all I can challenge you guys to do because there's literally no way I can teach you everything. What I do want you to know is you saw how I Googled Keras max pooling, right? And then I come down here, I skipped all the rest of that stuff and I come right here. This is what I want to see. I want to see the documentation for what are my arguments. We read it, we solved the problem together. Is everybody cool with that? Right? That's really all you can do, okay? All right, now dropout. The idea is that with dropout, okay, we have all these parameters, all these numbers that we're learning along the way or whatever. And dropout is going to drop 25% of them. The least valuable 25% of them, okay? So what we're gonna do is to prevent overfitting, that's part of what dropout does, is to prevent overfitting, we're gonna drop 25% of them that are not really being useful. So let me give you an example. Let's say I had several parameters. It's raining outside, okay? It's cold outside. and your favorite baseball team won the World Series. Okay. All right. And the prediction needs to be, should I take my jacket or not? Should I wear my jacket or not? Okay. Well, which one of those parameters has nothing to do with the final prediction?
Favorite baseball team.
Favorite baseball team has nothing to do with that, right? So eventually, basically, I can start to drop parameters along the way that are not contributing to the final decision. Does that make sense to everybody?
I figured out where I got the confusion from. If you want me to clarify.
Please,
So the pool size doesn't have to be a tuple. It can just be a scalar
Straight
number,
number.
just a single integer.
Yeah.
And then the example that I was looking at had the pool size equals 2, comma, stride equals 2.
Oh.
And so when I was looking at that, I thought that was, but it was a different way it was written, a different syntax. So that's where I got the confusion from.
Now I did know that. Okay, so you don't actually have to have two values here. You can just do a single value. Now let me ask you this: since you're looking at that, Michael, does it have to have parentheses around that if it's a single value?
Let me look.
I did know that you can use a single value here. So for example, if you just had 2, it just automatically defines this little thing as a square, 2 by 2.
So you don't have to have parentheses if you use just the 2.
Okay, so it's just that single scalar, pool size equals the number 2, right?
Yeah, exactly.
Now again, I don't want anybody to get too wrapped up in what we're doing here, okay? Remember, you're gonna have your own code soon, and that's gonna come from me. And that code, you're gonna be able to go through that code step by step, and you're gonna be able to make sense of everything. It's all about exposure. In my opinion, exposure can make anyone a genius. The more you look at something over and over and over again, the better you're gonna get at it, okay? So let's keep that in mind here. So now, we've done the max pool, and then we had a dropout. Now notice here, this dropout is not over here. Does everybody see that? So this morning when Michael asked me about something about biases, Dr. Lobo said, did you add a bias or whatever? Here's what I want to say to that. This dropout that we have on there, that is part of the art side of deep learning, okay? That is part of this trial and error business where you're going to add in dropout, and then you're going to take it away maybe, or you're going to decrease and increase the value, and you're going to find out what performs the best. Does that make sense to everyone? Okay. You can't know those things out of the gate. It's literally impossible for our brains to fathom whether it's good out of the gate. Why is that true? Because this dropout value is operating on, in this case, thousands of parameters, not millions, but it's going to operate on a lot. So there's no way for you to actually calculate all that stuff in your head. Now, let me say this. Dropout usually happens after a max pooling like this, okay? So there are certain things you need to know. For example, where does dropout usually happen? Now,
Can I ask, what is dropout? We've never gone over exactly what dropout is.
So this is me being a little bit of an a-hole. Did you miss that whole thing we just talked about? If you did, it's okay. I'll do it again. But remember the whole thing where I said, like, your favorite baseball team?
Oh, okay. Yeah. Right. Okay. But, okay.
Okay, so here's the idea. Here's the idea, is that there are parameters that are not contributing to the final prediction, or they're not contributing very much. So what we're going to do is we're going to drop those. And we're going to drop those to prevent overfitting and to reduce the number of parameters in our model.
Okay, so is that like a limit? Like if it's below this, then it gets dropped, or is?
No. That, well, in a way, I guess, but this is a percentage. You're going to drop the 25% least contributory parameters in your model.
Okay.
Do you see what I'm saying?
Yeah.
Okay, so let me see. Hold on one second. All right. Yeah, so we're gonna drop that stuff. Okay. Now let's continue here. Okay, so
Sorry, I just had a quick question.
go ahead.
So when you say parameters in this case, is that
Yeah.
referring to each value in this table of numbers that we're generating, or is that referring to like each table as a whole that we're
Parameters are going to refer to, okay. So here's what's going to happen. You're going to start with this image, right? And then you're going to take your filter and you're going to slide it along that image, right? In convolution. You with me? Okay. Okay. Now you're going to slide it along that image. Well, let me ask you this. What values went into your filter?
it would be each of the values in the 3x3 window, right?
Exactly. And where did those come from, though? That's my point.
Uh,
Well, when a mom parameter and a dad parameter fall in love. No, I'm just kidding. I'm just kidding. So where do they come from?
it would be from whatever input image is being provided from the previous layer.
Well, okay, so and it's okay. What you're doing is exactly what I want you to do, because you're just going backwards one step at a time, right? And I'm going to keep you going until we get there. But the point is, at some point we started with an image and we had a filter that had no numbers in it yet. Where do those numbers come from?
That would be it was in the data preparation stage.
Nope.
Oh,
Aren't the numbers in the filter what get learned by the model?
But where did they come from?
Back propagation?
Well, okay, but to think about it, you've just started your model, right?
They're going to be random at first, right?
There you go. That's exactly right. They are randomly generated in the beginning. And the type of randomness that you choose, there's different ways of choosing that that randomization, okay? But here's the point. Those are the parameters that we're learning, all right? So in the beginning, the parameters of our model are the numbers inside of those filters. So you're going to take, this is the very first thing you're going to do, the very first image, whatever. Here's your first image. And you have a 3x3 filter that you need to slide along that thing, right? And you're going to multiply each one of the numbers in that 3x3 by the numbers that are in the image at that corresponding location, okay? And then you're going to add them together, and that's going to be the new number. So to start the whole process, we randomly choose numbers that go in that 3x3. So you're going to take your image, it looks like this. You're going to take your 3x3, and in the beginning, those numbers get randomly generated. And you're going to take them, you're going to slide them along. Okay, just pretend we only have one filter for the whole thing. You're going to take it and you're going to slide it along, right? Next step, you're going to take the filter, slide it along. And at the end, you're going to get a prediction. Is this a cat or not? Well, if it's right, then you're going to, when you back propagate, you're going to keep the weights the way they are in that specific parameter. Does that make sense? If it's wrong, we're going to update them as we go backwards. Okay. We're going to update them so that the next time around, they're more correct towards the fact that this is a cat. Does that make sense to you?
yeah. I guess I'm still a little like I understand the overarching concept that you just
Which is the
explained,
most important, but okay.
yeah, but like the word parameter itself, I'm still is that referring to each neuron in the neural network, or is that referring to the data that is being provided into them?
It's not the data that's being provided into them. It's the number. So basically, you can think of the neuron, and basically you're going to have an input and an output, right? An input and an output. The number that takes your input, you can kind of imagine it's going in from the top. The number that takes your input and makes your output, that is the parameter.
Oh, it's the number that is like, it's the modifier that exists within.
Pretty
the-
much, you can think of it like that.
Okay, I
Exactly
see.
right. Okay. All right. Now, so here's what's going to happen. We're going to do some convolutions here. We're going to do a max pooling. Now, I want to say this. Somebody made a comment earlier about max pooling, but in general, max pooling is a form of downsampling. That is the original purpose for max pooling. Now, it can also prevent against overfitting, sure, but the whole point is to downsample these things because the original images are bigger than what we want in the end. Especially if you think about, imagine you have a 500 by 500 image, or these days, imagine it's like 1,000 by 1,000 image, okay? Well, that 1,000 by 1,000 image, does everybody feel comfortable about this idea of when I say flattened? Does anybody not know what that means? It's okay if you don't, I can tell you right now.
I'm assuming you mean flattened as in like you take the 2D shape and you just kind of take the rows and string them along.
Yeah, or the columns and you stack those on top of each
Right.
other, right? So you take the first 1,000, the first column, and then you take the next column, you stack it here. Then you take the next column, you stack it here. So eventually you're going to have this 1,000 times 1,000 dimensional vector that's up and down. Now it's a vector. It's not a matrix anymore. Does that make sense?
Wait, are you also doing that with the 3 channels?
Yeah.
Okay.
Yeah. That's kind of what I was saying earlier, like when we talk about the depth of the image itself. You almost just kind of want to ignore that there's 3 channels in a way, okay? Because we kind of treat it as one unit, the image. Okay, so we're going to take all that stuff and we're going to flatten it. Now, if you took 1,000, sorry, I got the hiccups. If you take 1,000 by 1,000, right? So you're going to have what? 100,000, is that right? 1,000 times 1,000, add on the zeros, you get 10,000, 100,000, right? You're going to have 100,000 element vector.
I think that's 1,000,000. Well, it doesn't matter.
It doesn't matter, you're absolutely right, but now I have to know. You're right, it's 1,000,000. Let's see, 1,000 times 1,000. Oh, sorry, 1,000 has 3 zeros in it. I only added 2. Thank you. Thanks. Okay, so you're going to have this 1,000,000 dimensional vector. Now, but think about classification, especially in the case of 10 classes, okay? In CFAR 10, you have 10 things, right? Car, truck, dog, cat, plane, whatever, okay? That 1,000,000 dimensional vector has to be reduced down to a size of 10 by 1. You with me here? 10 by 1. That way we can see that which one of the numbers is the highest, and that means, oh, it's a cat, oh, it's a dog, whatever, right? So this idea of max pooling meaning that we're going to take the maximum value over each one of those things. It's the most characterizing value. You can also do min pooling or whatever, but that's not common, okay? So we're going to, then once we do all those things, we're going to get down here, we're going to flatten our vector, right? So by doing this max pooling, okay, it's keeping our image from just getting away from us, right? It's going to use this downsampling idea before it gets away from us. Then we're going to flatten it. And once it's flattened, now we're going to start to do these dense layers, okay? Dense meaning basically a fully connected. Now, is anyone unclear about what I mean by fully connected? It's okay if you are, just tell me now so I can just take a little dive into it.
All the nodes in this layer are connected to all the nodes in the previous layer.
It's right. It literally means exactly. Okay, so you have a vector. Here's a vector. Right. And then in the next step, we're going to have some smaller vector. Every single one of the elements here It's connected to every single one of them over here. So let's say we have 100 here and we have a 10 here, okay? You're gonna go from this one, you're gonna go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then in the second element, you're gonna go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then the third element, you're gonna, does that make sense to everybody? So you can have lines connecting, kind of like the green lines in the background. Actually, that's a great example.
Robert?
Okay,
Okay, so in CNNs, we start by doing convolution layers, then pooling layers, and then we do the dense layer. Okay, so the way I'm used to CNNs or neural networks in general is that there's like a bunch of circles connected together.
circles?
Yeah. You know that, like the image of neural networks.
Oh, like the neuron.
Yeah. The neurons. Is this dense layer that neuron step?
That's exactly right.
Okay. So it's different now. So now we have convolutions, we have pooling, we have dropouts, we have
Yeah.
flattening, and then we enter the neural networks.
That's exactly right.
Yeah, it's because I've only seen it in images, and like everybody has that image of those fully connected layers of neurons.
Yeah. Okay. So neurons, right? Those are, personally, if I were you, I'd throw the idea of neurons away. I don't think it's useful in any way. I think it's a weakness that we had, that we were trying to say, oh, these things mimic the brain. I mean, it's not true. You know, science has come to the conclusion that it's not true. And in my opinion, it doesn't help. It's just all equations. Memorize the equations and memorize the convolutional method and the fully connected method. And that's what you need to know, right? I'm not saying anything to you, Zane. I'm just saying in general, my experience is that the idea of a neuron doesn't help at all in the end. Okay. But here's what I do want to say. You're absolutely right in the sense that typically the format is this. You do some max pooling. You do a convolution, then you do a max pool. Then you do a convolution, then you do a max pool. Well, you're also doing an activation function in there like ReLU, okay? But that's all included in a single line in here. And then all of the convolutions are gonna happen over here, right? This is at the beginning. You're gonna take your image, you're gonna go through the convolution and max pooling stages, right? And it's shrinking this way, but it's increasing in this way by the filters, okay? And then what's gonna happen is, then you're gonna flatten that whole thing, and then you're going to go through some fully connected layers and it's going to start to shrink. And then at the end, in the case of classification, you're going to end up with a vector that is the size of the number of classes that you have. Does that make sense to everybody? That is the overall arching structure of what we're talking about here, okay?
So on that note,
Yep.
on our last line, we have dense with the input 10. Is that what defines the size of our output vector at the
Correct. Yeah. So we're going to end up with a size of 10 output. Okay. So what you do up here, okay? You say model is sequential. That means we're going to use the sequential model, which that's the way you should do it right now, especially with Keras. I'll show you a way to do functional with PyTorch. But personally, I think right now, for where you guys are at, I think you should stick with the sequential model because the code reads easier, right? When you look at this code right here, to me, this code says exactly what this says right here. Does everybody kind of agree with that? But if you look at this, see this, you could consider this a block, okay? What do I mean by a block? Well, conv2d, max pool, dropout. It's repeated here, conv2d, max pool, dropout. Does everybody see what I mean? So you could use something functional, meaning you could write a function that adds a block that looks like this. And then you could say, hey, add block 2, add block 1, add block 2. It would be unnecessary. It would be overkill in this case because we only have 2 of those blocks. But if you had 20 of those blocks, or even 10, even 5, it may make more sense. But for where you guys are at right now, I think the sequential model is the best because the code reads the easiest. Okay. Now let me contrast that with something in PyTorch real quick. Okay. I'm going to give you an idea now. And I know we're kind of going back and forth between PyTorch and Keras. Okay, it's not so much the syntax I care about for each one of the frameworks. What I do care about is syntax for Python and just overall structure of code. Those are the important things, okay, right now. Now, if you'll notice here in this PyTorch code, see how I've defined this kind of like this dictionary here of VGG11, VGG13, VGG16, right? Now, check this out. If you look at this code here, blah, 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 look at this function I've written right here. Make layers. Okay, that's exactly what I'm talking about in this functional block adding business. Okay, now compare that. Okay, so this is class VGG, right? Now, look what I've done down here. As an example of the above, here is a VGG16 hard-coded, which is easier to read. So compare this code right here also is the same as this code right here, okay? But look how much easier it is to read. Com2D, batch norm, Com2D, batch norm, max pool. Com2D, batch norm, Com2D, batch norm, max pool. Now, you see what I mean by blocks? Like it's kind of the same thing happening over and over again. So you might want to use something that's going to be functional, but in the beginning, I think you should stick with this hard-coded format. It's much easier to read. It's less confusing. Okay, so that's kind of the idea. So you see how I have Com2D batch norm, Com2D batch norm every time, okay, over and over again. Well, at some point, you could just call that a single layer. This is a layer. And look how many of those layers I have to do, right? I go all the way down here, okay? So that being said, I think at this point of the game, your best approach is to keep this nice sequential model, nice sequential approach. Okay, you're not going to be doing anything super complicated. And in the event you do want to do something a little bit more complicated, the person you're working with will help you do that. Okay. At this point, keep it like this. It's easier to read. Okay. So notice how in this code, we defined our model, right? But defining the model, it's just like defining a class, right? We haven't instantiated that object yet. All we've done is defined that object, what it's going to look like when we do instantiate it, okay? Now, like I talked about earlier, usually you want to have a separate code for model, right? Now, we haven't done that here because this is so little code that it didn't warrant a whole file for itself. Does everybody feel me on that? Okay. This doesn't warrant an entire model.py because it's so little code. The overall code itself is so short, it's not worth doing separate files, etc. Okay. But for good practice, you can start doing that right away. Now, here we're going to define our optimizer. SGD is equal to SGD. This is stochastic gradient descent. Okay. Now let's take a look. Let me go back one and see. Here, okay, look at the beginning of the code. Import numpy as np, we've talked about that. Import Keras. From Keras.models, we want sequential. From Keras.layers, we want dense, dropout, flatten. We also want Com2D max pooling. But here, if you'll notice, from Keras.optimizers, import SGD. That's why we're able to use the name SGD right here, okay? We don't have to say Keras.optimizers.sgd because we've imported it. Is everybody cool with that? And we're going to call it lowercase sgd. So we're going to bring it into our Python namespace as lowercase sgd. We're going to instantiate this object as lowercase sgd. We're going to use a learning rate of 0.01. Okay, 0.01. That's still a little high for some models, but I think in this case, it's probably okay. DK, don't worry about that. Momentum, you don't need to worry about that. Nesterov, you don't need to worry about that. Okay. For your purposes, just leave these the same. Okay. Model.compile. Right. This is where you're going to build the model. You're going to tell it which loss function you would like to use, categorical cross entropy. And here we're going to say optimizer is equal to SGD. Now, tests. Why did I basically just define lowercase sgd and then I just write it right here? Why didn't I just take that and put it right here.
I think maybe you could have, but this way it's simpler, so it's not like a really long line.
It's exactly right. That's all it is.
Okay.
Nothing fancy here, folks. I mean, you literally could have just taken this and put it right here. But now it's just not a long line. It's exactly right. Right. And this way it allows us to kind of pull this optimizer out and have it in a separate line so that we can kind of put these parameters the way we want them. And it's not getting all caught up in this model.compile business. Okay. Model.fit, we're going to train our model right here. We're going to pass in our X data, which is the images. We're going to pass in the corresponding Y labels, right? Is this a cat? Is this a dog? Whatever. Batch size and epochs. Okay. All right. So let's talk about batch size for a minute. Have you guys talked about batch size with anybody else? No. Okay.
No.
So let's talk about this. So here's the idea. Let's say you have a data set. Let's say it's CFAR 10. Okay. Actually, let's be simpler. Let's just say you have a data set, 10 classes, right? Does everybody understand what I mean when I say a class? 10 classes. Okay. And let's say you have 1,000 images total, evenly divided over the classes. So that means each class has 100 images, right? Well, so that means you have 1,000 images. Well, at present, it's not possible to pass all 1,000 images into a model, computationally speaking. And what in the beginning, what we found was that it made more, it was more computationally feasible to pass in smaller batches of images instead of trying to pass in all 1,000 images. At all 1,000 images, there's not enough memory on your machine to keep all of that in its head, right? When you start to consider how many parameters there are for each image, right? We talk about what are these parameters, right? All these parameters. Well, think about this one up here. Okay, we have 32 3x3 filters, right? So that's 9 times 32, 270, 288, something like that, right? There's 288 parameters. That's just for one, that's just for the first image, right? And then it's going to do over the next image or whatever. And then we're going to, well, it's not really true what I'm saying, but it's going to start to learn these things for each, and then you're going to do it again, and then you're going to do it again. Okay. So my point is this, is that by passing in 1,000 images, there's not enough memory on your machine to keep track of all that stuff. So what we're going to do instead is we're going to do what's called a mini batch. Instead of taking 100 images from each class and trying to squeeze all of that into our machine at one time, we're going to take 10 images from each class. So how many images end up into our model at a time, Robert?
Maybe 32. Or at least what I'm looking at here.
Okay, all right, let me ask the question again. So instead of trying to squeeze all 1,000 images into my model at a single time, okay, I'm going to take 10 images from each class and I'm going to put that into my model. How many images are going through in each mini batch?
If there's 10 classes, it's 100.
You got it. Okay.
Yeah.
Now there's 100 on each mini batch, right? But there's a
And you
total
run it 10 times to get.
and you're going to run it 10 times, right? So there's going to be 10 runs per epoch. Okay. So what that means is that there's going to be 10 batches for a single epoch. Now, here's the way you can think of an epoch. An epoch is when your model has seen all of the images in your data set. Does that make sense? So in this case, each mini batch is only going to have 100 images, right? So you're going to take 100 images, pass them through. Then you're going to take the next 100 images, pass them through. Then you take 100 images, pass them through, right? You're just 10 times. Once you've done it 10 times, that means you've done a single epoch. Does that make sense to everybody? So in an epoch, that means you've seen the whole data set. Okay, is that good? Okay. Yeah, so here, okay, I see what you're saying.
Yeah.
Batch size. Yeah. Sorry, go ahead.
I guess this is just a number thing, but is it reasonable to expect the model to learn good weights when the learning rate is only 0.01 and you have 10 epochs?
As opposed to what?
A larger number of
Okay.
epochs.
How many epochs are we using here? 10? I mean, with this small, I mean, these are just toy numbers. This is all you can, I don't even know what this is for. You know what I'm saying? This is not real. Nothing's real here. Like for example, I don't know how many images are in this data set. Did we define that on the previous slide?
Can I chime in for a second?
Yeah, we have random data here, right? So we've randomly, looks like we have 100 images. So 100 images over 10 epochs. Yeah, that's probably fine. Right. Go ahead, please.
So I actually toyed with that as part of my experimentation over the weekend, and it just kind of like the accuracy of the model will increase, and at least for me, it was kind of logarithmic.
Yeah.
However, the actual like validation and test accuracy like increased and then like kind of peaked and then went down a little bit, just kind of stayed there. So like you're just kind of overfitting past a certain extent, at least for these models. But I know it's just another thing you can mess with.
It's another thing you can mess with. That's exactly right. So we have this idea of hyperparameter. Okay. Have you guys talked about hyperparameters yet with anyone? Anyways, I'll talk about it now. So now that we've been through enough here that I can start to talk about hyperparameters. Hyperparameters, hyper, meaning we're going to choose them before we run our model. Okay. Hyperparameters are typically things like how many epochs will I run? What learning rate should I use? What's my batch size? How many convolutional layers will I use? Right? These are things we choose in advance of actually running our model, right? So the idea is that because, and that's why you can't just use brute force to do all this stuff, right? You can't just use brute force to come up with the best learning rate. And there are things that are like that. But because each one of the models that you'll end up using will have millions of parameters, well, then if you change your learning rate from 0.01 to 0.001, now you have another million parameters that you have to deal with, right? And then let's say instead of batch size 32, you go up to batch size 40, right? Well, now you've changed your learning rate. So you have a million for the first one, a million for the second one. Now you got to change your batch size for each one of those. Million. Got to have a control. Right. That's why brute force is not really useful here, because we're dealing with millions and millions of parameters for each one of these things. Okay. So it's not feasible to just attack it in that way. So what you'll start to learn is, because I haven't even listed all of the hyperparameters. Another hyperparameter, for example, is dropout. First of all, should I use it or not? Then once I decide to use it, what number should I insert here? Okay. So for example, typically the way it works is you keep a higher dropout at the beginning of your model. Or no, I'm sorry. You keep a lower dropout at the beginning of your model, and then you increase dropout. Sorry, I had it backwards. You have a higher dropout towards the end of your model when you're trying to make those predictions, okay? When you only want the things that are directly influencing your prediction the most, right? So you can see here, dropouts 25, drop the lowest 25%, drop the lowest 25%. Here we're starting to drop more, right? I only want those things that are directly influencing my prediction, okay? So the point is we have all of these hyperparameters that have to be chosen in advance. So as you can see, the idea of convolution, the idea of max pooling, those things aren't really all that complicated. So the question becomes, then why are people in this field making so much money? And it's because until you have the experience of keeping track of all of these hyperparameters in your head and knowing when you should adjust one and not another, or just two, and et cetera, those are things that can really only come from experience. Does that make sense to everybody? Okay. It really is a numbers game at the end of the day. So let's take a look at what's next. Simple MLP network, functional model. Okay, we can take a look. So here you can kind of start to see how, instead of using this this approach of model.add, okay, notice how we've defined X here. First of all, you take inputs. Okay, so I guess when I was showing you the functions earlier inside of PyTorch, remember this guy, an actual function? That's not what it means, I guess. So what it actually is referring to, and this was my mistake, what it refers to is actually, see how this is a function of the previous input? So you define inputs here, and then you take inputs and you put it into this layer. You define that as X. Then you take that value, whatever it is, and you put it into the next layer. And you run that. Does that make sense to everybody? Do you see what's happening here? If not, speak now or forever hold your peace. Right? So it's functional in the sense of a function like f of x, right? So you're taking the previous value and you're plugging it into the next function, right? And then you get your predictions, and notice you're putting x in here, right? So model equals model, right? So then you're going to have the inputs and the outputs. This part's pretty much the same as the previous part, as is model.fit, okay? Yeah, each layer explicitly returns a tensor. You see how that's happening here? Okay. Rnns, I don't think we're going to do much with this. This is something that Dr. Rawat will talk about later in the week. I don't think we're here yet. This is an important slide, okay? So for the most part, you guys probably won't use any one-dimensional convolutions while you're here. One-dimensional convolutions act on things like audio signals and NLP stuff, right? Natural language processing. So like word to vector, right? Where you're to act on those vectors. Two-dimensional convolutions are going to act on images, okay? So here's the difference. One-dimensional convolution is going to act on a vector, right? Here's your vector. So your audio signal can be represented as a vector, right? Especially because you use these things called Mel frequency cepstrum coefficients. Nothing you need to worry about, but those are basically represented. It can be represented as a vector, okay? Or a one-dimensional thing. Here, we're going to deal with two-dimensional convolutions, okay? Images, right? So you can see I'm going to use two-dimensional convolutions on this two-dimensional thing, right? But then I'm going to use three-dimensional convolutions when I have multiple images. That means I have this depth, okay? Now you can actually use a three-dimensional convolution on an image, but we're not going to talk about that right now, okay? Pooling layers, max pool. This is an nice little graphic, okay? This is what we talked about earlier. When you have pool size, okay, so this is good, okay? So first of all, pool size here means we're going to use a 2x2 filter, right? So you can see how the color is like pink here, and then the color is green here, right? That's, you took your filter. And since we said strides equals none, what that means is it defaults to a jump of whatever number is over here. So see how this is 2? So basically you're going to take it, you're going to run it in this area, and then you're going to jump over 2. So it's whatever section was here, you're going to go 1, 2, and that's now right here. Okay. And then this green number, whatever the maximum value here is, you're going to take 8 and you're going to put it here. And then you're going to move it over here. And then you're going to jump 2. You're going to get this. Is everybody clear with this? Right. Okay. Padding valid means that you don't use any padding. If you say same, it will just use whatever padding is necessary to keep the output dimension the same. Okay. Average pooling. So Lee, Howell, since we talked about max pooling earlier, you want to take a stab at what average pooling is?
Are you asking me, right?
I was not, but sure, you can go. Lee,
Oh,
Lee
okay.
Meow.
Yeah, sure. So average pooling, instead of getting the largest number out of 4, I think you'll calculate for the average value of the 4 number and use that number instead.
Say it one more time, slower, please.
Oh, I'm sorry. I mean, instead of using the maximum number of the 4 squares, and you're actually calculating the average number of the 4 squares and use that one instead for the average pool.
Yep, that's it. Hold on, one second.
So average pooling is just like generic downsampling then?
You just take the average over the square. Okay, then we also have upsampling, which you may use that. I don't think so. But you can see what happens here. Does everybody get the idea? It's literally kind of like the same thing in reverse, but keep in mind, okay, like see how we have this little pink square here? This pink square came from these 4 pink squares, right? Well, unless there's no way in the case of upsampling, unless you had downsampled, then you wanted to upsample. But in the case of upsampling, there's actually no way to replace the original values here because we haven't stored that anywhere. There were no original values. Does that make sense? That's why you have to take whatever values here in this gray square, like for example, 6 in the pink square, and 6 is going to go 6, 6, 6, 6. It's going to go there, right? 8, 8, 8, 8. Does that make sense to everybody? All those numbers have to be the same because there was no way we could know. There is nothing that was there before. Okay. General layers. So if you guys are interested in reading a little bit more about the optimizers, you can go here. Okay. In my experience, you'll probably use Atom. Okay. Or whatever's hot right now. You'll find that based on, like, for example, you'll find some code you like for something, and the idea is that the person that you're doing a research project is going to give you some code, and then you're going to try to modify that in one way or another. In my experience, the only time you really need to play with the optimizers a whole lot is if that is the name of the game you're playing. In other words, you're trying to define or build a new optimizer. If you're trying to publish a paper, for example, we started with SGD, right? And then somebody came along and they said, hey, I'm going to build Atom. In other words, the name of their game was defining a new optimizer. Does that make sense? Unless the name of your game is defining a new optimizer, you're not going to have to play with these a whole lot, okay? That's my experience. Could be wrong, but okay. Loss functions. So here's your mean squared, error, chew.
Did you want?
No, didn't you ask about a loss function as a mean squared error last week?
I don't think so.
Somebody did. Maybe I got it wrong. Categorical cross entropy, where K is the number of classes. KL divergence. You haven't talked about KL divergence yet. KL divergence is going to measure the difference between two probability distributions. Okay. So basically you want to bring them, you have two distributions, you want to bring them closer together, you want to minimize that error. Again, all right, now, okay. And some people may, a lot of people would probably, Dr. Lowe would probably disagree with me, okay, but here's my idea. In my experience, unless the name of the game that you're playing is building a new loss function, this is not something that you're going to need to work with a whole lot, okay? You're going to have a loss function, and if it doesn't perform well, maybe you'll try something else, okay? Usually certain loss functions are used for certain types of problems, okay? That's pretty standard. But unless you're trying to devise a new loss function, this isn't something that you're going to really jump super deep into, okay? Okay, there's that.
Is this the KL divergence? One distribution is the probability distribution that gets output from the model, and the other one is the true probability distribution? Is that?
Well, if we knew the true, when you say the true, you mean, first of all, I guess it depends on the context. Like the true distribution based on the parameters. I mean, based on the labels.
Yeah. Like I guess it would be like 100% car and 0% cat, and then your model might say like 80% car and 20% cat. That's
probably the most common use, yes. You're trying to minimize the distribution, minimize the distance between the true distribution of from your labels, right? That's probably the most common case, yes. In my experience, the only, but I'm sure there's others. Here, okay, here's some, so basically here's how it's going to work. Okay, so you're going to train your model, and when you train your model, then what do you do with that trained model, Brian?
Well, if it's efficient, then we would want to keep it.
Yeah, you want to keep it. It's exactly right. And then once you've kept it, what do you do with it?
Maybe try and deconstruct exactly what went right with that specific model.
It's not a bad idea, but in general, the idea is that you would want to keep that model for predictions on future data that comes along your way. Okay, I mean, because we can talk about, you know, the stuff that we're going to do here, but that's really irrelevant, because really the point of all of these things are to be used in the wild, in the real world, right? So a really real world problem was a year or two ago, somebody in the lab was working on, I think it was Florida Department of Wildlife or something like that, whatever it is. But they were trying to, there was like animals running across a road, right? And they were trying to minimize the animals getting hit or something like that, determine whatever, but they had to determine what animal was running across the road. So basically a classification, right? Is it a panther, a black panther? Is it a possum? You know, whatever's running across the road. And I say the panther first because I think that was the one that they cared about, like, is it running across the street in this area or not? But anyways, it was just a classification problem, right? So they had, you know, all this data that they had compiled over the last couple of years or whatever. So that's the point. They trained their model. They wanted the model. They trained on these last couple of years worth of animals running across the road. And then what they were going to do is they were going to use that model in the future at predicting what animals running across so that they can keep track of 10 panthers ran across the road, 3 possums ran across the road. You see what I'm saying? So that's the whole point. We want to train these models. If they're good, we want to keep them so they can be used for any future data that comes along our way. Okay. Now, let's say, for example, you train yours in Florida, maybe, but then I wanted to use the same thing in Alabama. Well, so the question is, you trained your data on the roads in Florida, but then I want to use it in Alabama. Okay. Now, in some ways, this isn't a great example of domain adaptation, but basically the point is that if you trained your data on in a certain place, or excuse me, if you trained your model in a certain place with specific data, and then you want to take that model and use it in another place, that's the point. That is called domain adaptation or domain transfer. Okay. So for example, let's say you trained it on, I don't think I need any more examples, but the point is that you trained it on one set of data, and then you want to use the model trained on that data on and tested on another set of data. Does that make sense to everybody? You guys see what I'm saying? Right. That is called domain adaptation. Okay. So here, you can just read through this. It's pretty straightforward. So this is how we save those models. Okay. Now, when we talk about saving the model, what am I saving exactly?
The parameters and their values. And the structure of the model.
Yeah, exactly. So we're gonna save the structure, and we're gonna save, we're gonna save the value of the parameters in our model. Well, when we talk about the parameters, what are we talking about? Sanjay?
We're talking about the basically the modified, I don't know how else to describe it other than the numbers within the nodes that are used to predict or like modify the incoming data and make predicted outcome.
Yeah, so basically for the most part, what we're doing is we're saving the filters. Okay, that's the bulk of the parameters that we're saving. So those are called weights, right? And we're also saving the biases. Okay, we can talk more about that stuff later. You're also saving the, so here you can see the things here. Architecture of the model, right? So what did the model look like? What was the shape? How many convolutions? Stuff like that. You're going to save the weights and the biases, which I think you probably should have talked about with Dr. Love already a little bit. Oh my God, look at that cat. Is that a baby kitten or is it just far away?
It's just far away.
Oh my God, it looked like a miniature cat to me, and not a kitten, like just a miniature cat. Okay, and then you're also going to save the state of the optimizer. Okay, we can talk more about these things later, but these are the things that get saved. Okay.
Isn't this the model.summary, or it's more than that?
More than that. So we're going to do something very similar in PyTorch. Most of these things, most of these ideas are going to be replicated in PyTorch. Okay. Most of these ideas are going to be replicated in any deep learning framework that you're going to use. So the syntax to me is less important than the ideas that are behind them. And the point that the idea that's behind all of this is that you can save a good model and then you can load it to be used later. Does that make sense to everybody? That's the point. If you know that it can be done, then you can just Google how to do it when you need to do it, right? And this is how you do it in Keras. I'll show you how to do it in PyTorch later.
Quick thing.
Yeah.
There's actually an automatic callback you can add to Keras models to save them when certain conditions occur, or just like every few epochs or so. So that's a cool way to automate it.
Say it again.
You can
I'm familiar
actually
with callbacks.
Yeah, you can automate the saving of.
Yes, you're right. You are correct.
It's kind of a useful feature if you only want to save when the model improves, for example.
That is true. That is true. In TensorFlow, I have no idea what it looks like. However, in PyTorch, in the code that I'll give you, I actually have something in there for that. Okay, but you're correct. No way. What is this? Kitty cat hour. So in Keras, there's just literally a single line. You can just say callbacks equals something improvement or something. I can't remember exactly. We'll look at it later. Extracting features from pre-trained models. Okay, so a pre-trained model, right? So let's say this, okay? So a common thing that people do is they pre-train their model, okay? What do I mean by that? Well, okay, you take a model, let's say you have a model, and let's just call it VGG16 because that's what we're looking at here, okay? And by the way, you can now see that you can import VGG16 into your Keras model. So you remember how I told you guys to do all of like the different layers and all that stuff? And you're going to do that. That's good. I want you to do that. But you can literally import models with a single line. So that's the one you should probably, you can, when you talk to Dr. Shaw, you can say, hey, I didn't expect, I wanted to see the effect, according to assignment 1, I wanted to see the effect of different layers being added and taken away from a model, as well as more and less data. However, the performance was very low from that, which is okay because it was just an experiment. But finally, I decided to use a VGG16 to get a performance of. You see what I'm saying? Okay, that's how this discussion goes. Okay. So here's the idea. Okay, you find yourself, you have a bunch of user images from some website you're running, okay, and you want to classify those, okay. So should you? But let's say you actually you have none of your data is labeled. Okay, that's the problem. None of your data is labeled. And what you want to do is you actually want to start classifying that data right away. And you don't want to label your data. Okay. So would it make any sense to take this VGG16 model from scratch and just start running it on your data? No, that wouldn't make any sense, right? Because your model starts with randomized weights. You see what I'm saying? So it will make a prediction, but the prediction is going to be wrong because you haven't learned anything. You haven't taught that model anything. So what people will do is they will pre-train a model on another data set. So for example, think about what we're doing, and this is a kind of another form of domain adaptation in a way. Okay, what are we doing? Well, we have a bunch of user images of animals and cars and food and stuff like that on our website, right? So the common data set that people will use is called ImageNet. And it has like more than 1 million images. I don't remember how many exactly, but you're going to use ImageNet and you're going to train this VGG16. Does that make sense? You're going to use a data set that's not your data. It's just a common data set that has a lot of different stuff inside of it, right? And you're going to train this model so that the model doesn't come to you stupid. It doesn't come to you just blind and it doesn't know anything. It's going to come actually having some real world knowledge about what things look like. Does that make sense? Okay, that is called pre-training a model. Does that make, is this unclear to anybody? Because this is an important point.
How similar does the pre-training data have to be to the data you're trying to use?
It's a very idealistic question that you're asking. I mean, if you could choose, you would want it to be the exact same, right? So how similar does it have to be? Well, I would assume there's probably some correlation between, oh, hold on, somebody's knocking on my door. Okay, so I mean, the correlation between how different the data is and how different your data is probably is directly correlated with the amount of error that you'll get or the loss of accuracy.
Well, I guess what I meant was that if the pre-training data isn't clearly similar, would it still help?
Yeah,
at all?
absolutely yes. Absolutely yes.
Okay.
Almost always. I mean, the thing is that like you almost, unless you have your own data set that you want to train on, right? And sometimes even then, you almost always want to use a pre-trained weights, a pre-trained model, because at least it's not walking in completely blind, right? You want it to have some idea, because the idea is that think about these minimums that we're trying to achieve, right? And we talk about the learning rate, and we're trying to come along and we're trying to get here, right? And so here's the minimum that you're trying to achieve. But if you're starting off with completely random weights, you may be starting way over here at some other minimum, which is not your global minimum, right? And you may start off in some completely wrong place. So by having these pre-trained weights, sometimes it helps us get a little bit closer to what may be expected in the end. And it will allow us to find those correct predictions at all and quicker. Does that make sense? Yeah. So almost always the answer to your question is yes. Almost always you want to use pre-trained weights. Then once you've used the pre-trained weights, okay, then what you're going to do, usually what will happen is you're going to have a pre-trained model, and then you're going to take your own data and continue training the model with your data, not the other data. Does that make sense to everybody? So it's like this. Okay, here's your model. Okay, it's looking like this, right? And your model only sees the ImageNet data set for the first part of its life. And then it grows up, comes to you, and it's never going to see its ImageNet parents again. Okay, it's never going to see that data again. But it still has memories of its ImageNet parents, right? ImageNet still lives in its heart. Okay, it still dreams of them at night, right? But it's never going to see them again. Now you've adopted this thing, and it's only ever going to see images of you from this point forward. Does that make sense to everybody? So you're going to train it on, I know it's sad. If some of you are crying, it's okay. But the point is that from now on, it's only going to see this new data, okay? Now, if it didn't have those parents in the beginning and it just lived in the closet, you know, and it never, whatever, some of those terrible cases you hear about children or whatever. But, you know, the point is that, like, for example, and let's say it learned English or Italian as a child. And then it comes to you and you only speak English with it, okay? The model. I mean, I would argue that once you know one language, it's easier to learn another language than absolutely never knowing any language. You see what I'm saying? Because there are structures that you are learning along the way, and those things are going to help you with the next one. Does that make sense? It's kind of that idea here. So you're never going to see your ImageNet parents again. Now you're going to start getting trained on this new data, your data, right? And that process is called fine tuning. Fine tuning. You're going to fine tune the model on your data. Okay. So in other words, it kind of is in left field right now because it only speaks Italian. You have to fine tune it to English. Okay. But it is better than it would have been otherwise. Okay. That's the idea. Okay. That's important. Everybody good so far?
Is that just a time-saving technique because there's so much time required to train the model?
It's definitely, it's not only for that, no, but I mean, it definitely can help us get to, you know, a accurately trained model on our data quicker. That's for sure. But sometimes your model may not be trainable on your data ever. Like with randomized weights, let's say you just try to train your model. Well, especially if your data set, I mean, there's really no chance. Let me see here. 14 million images in ImageNet, right? There's no way that on the website that you're running, you're going to have 14 million labeled images. You know what I'm saying?
So how would you be training the model on your data? You said that your data is unlabeled, so how would it
No, that was just a
calculate
random. That's just a random
Okay.
example. That's not fine tuning. That's just so like if you needed a model for the website that you're running and you didn't want to label any of the data, then you could just train it on ImageNet and see how it performs on your data, right? And when I say see how it performs, since it's not labeled, you'd have to manually compare. This says it's a cat. Oh, it's a cat. Oh, this says it's a dog. It's actually a truck. You see what I'm saying? In general, that's not how it's going to work. For you guys, what's going to happen is you're going to find a model. You could pre-train it on ImageNet or already be pre-trained on ImageNet. And then you start to train it on your data, but there's no way you're going to have 14 million images. Let's say you only have 1,000 images in your data set, right? There's no way you're going to be able to train your model with only 1,000 images from scratch. You're going to have to fine tune it. Okay, does that make sense to everybody? Okay. Import the network. So this is good, right? VGG 16. Specify the weights. So nice, right? You can literally do it in a single line. It's kind of like when you learn the power rule, right? It's like, oh, wow, you could have done this the whole time. The argument removes the classifier from the imported model. What that means is, okay, so you're going to train it on ImageNet, right? ImageNet has 22,000 visual categories, okay? So if it has 22,000 visual categories, in the very last fully connected layer of that model, what would be the dimension of the last vector?
22,000 by 1.
That's exactly right. 22,000 by 1, right? If there's 22,000 classes, if that was a one hot vector, then that means it's going to be 0, 0, 0, 0, 0, a 1 where the cat's supposed to be, 0, 0, 0, 0, 0. Okay. Well, you don't want that 22,000 vector, or it's called the classifier, the final fully connected layer of the model. You don't want that for yours because you only have 10 classes in yours. So you're going to throw that piece away. You're going to replace it with a 10 by 1 for yours. And now all you have to do is train that last layer from scratch. You don't have to train the rest of your model from scratch. Does that make sense? Okay. The input size of the image must be the same as what the imported model was trained on. Yeah, this is pretty important. For example, whatever the size of these ImageNet images that were being used in this VGG 16, right? You can't go back and change the input size of that model, okay? So for example, let's say you use 224 by 224 as the input for that model, right? You can't go back and change it to 128 by 128. Why can you not do that? Anybody want to weigh in on that?
Other than
The
the fact
weights and all the, oh, sorry, you can go.
Okay, I was just say, other than the fact it's not expecting that size, like this model has been trained on images of that size and that specific level of detail. So there's no way it could understand it.
Chu,
But
Chu, what were you saying? That was more, I think, more what I'm looking for.
Oh, I was going to say that like the weights and the convolutions to extract features are based on an image of that size, so they're not going to work effectively
Yeah,
on
so
each of a different size.
that's exactly right. I mean, you have this amount of parameters, okay? This amount of parameters, these parameters, remember how we talked about saving the model? When you save the model, you save the model structure, which has X amount of parameters. So if you go back and you change the model structure, which means the input, because if you change the input, it changes everything after that. If you change the input, then it changes the number of parameters. These aren't things that you can change. You can't take like, oh, I'll take only the center part of my parameters. It doesn't work that way. It all depends on the original image size, okay? Now, let me say this. Let's say you trained this model originally on, hold on one second. Sorry, I just had to lay down the heat. Dad life, okay. So let's say you trained this image. Let's say you train this model on 224 by 224, okay? And then you have images in your data set that are 1028 by 716, okay? What can you do to solve this problem?
Downscale and resize.
So there are two things I'm looking for. Those kind of are the same thing. Downscale is resize. I mean, we're resizing to a smaller size, right? So that's the first thing we're going to do. But the model here is trained on 224 by 224, and you have rectangular images. I have square images, right?
Well, you can crop out parts.
That's
of
an
the
option.
image.
Absolutely right. You can crop.
That's also why I included term resize, not just downscale, because you need to change the aspect ratio.
Ooh, boom, roasted to Robert. Nice. So
So
Yep.
is it true that humans can only process images of one size? Like, because even if you're looking at an image of a different size, your eyes are still looking at things that are not that image. Like your field of view is always the same?
I mean, I guess if you stand closer, but if you move forward and back.
Well, but like the size of what you're getting in terms of like.
Well, I guess let me say this. Okay, maybe what you're saying is true. Maybe. Not sure. But what I can say is that behind my machine right now, there's a blank wall. Okay. And on that blank wall, I could take an image that's this big and put it in the middle of that blank wall, and then take the entire blank wall as my image. Do you see what I'm saying? And that's part of the point. So what I wanted to say is yes, cropping is an option. You can take that rectangular image that looks like this, and you can resize it to a smaller size. And then you can crop out, which is very common, crop out a square region of 224 by 224, right? That's one option. The second option, that would be if you took the smaller side and resized it to 224 by 224, okay? But let's say you took the larger size and sent it down to 224, and you kept the aspect ratio. Then the other size would be smaller than 224. In a case like that, you pad with black, which means that you have the image somewhere in the middle of a larger black image, like I would my wall. Does that make sense? So you can either crop out a portion of it, or you can make it smaller and then put black around it like a frame and then send that in, as long as it's 224 by 224. Does that make sense? Okay. Those are some of the common practices. Okay, so I guess it's 1 o'clock now.